The previous video introduced integrals and integration. The integral of a function is just the area under the curve describing the function. This is easy to do geometrically for simple functions, but it isn't so easy for complicated functions. In this video, I'll show you how to use numerical analysis to approximate the integral of a function. The approach is actually pretty easy if you use a computer to do the simple, repetitive calculations. First, I'll quickly review integrals and their notation. Suppose we have a function that's represented graphically by this curve. We want to integrate the function between the values of a and b. The integral of a function gives the area under the curve representing the function. The integral of this function between a and b can be determined by calculating the area under the curve as indicated by this gray area. Mathematical notation relative to integrals is shown here. This is the symbol indicating an integral, where the lower limit of integration is a, the upper limit of integration is b, and the dx indicates that we're integrating relative to the independent variable x. In the previous video, we calculated integrals for a couple of simple functions based on geometrical arguments. That approach won't work well for a general function like this one. As an approximation to our geometric approach, let's divide the region under the curve up into n-1 little subintervals with their boundaries at n values of x. So interval 1 is between x1 and x2, interval 2 is between x2 and x3, and so on up to the n-1st subinterval, which is between xn-1 and x sub n. If we can calculate the area of each of these little subintervals, the total area under the curve will be the sum of the areas of the subintervals. So at the integral, I'll call it I, is a1 plus a2 plus a bunch of other little areas up to a sub n minus 1. More compact mathematical notation uses the summation sign. This indicates summation of all the areas, a sub k, for every value of k from 1 to n minus 1. The first step we'll do when estimating the areas of the subintervals is to determine the x and y values that define the boundaries of the subintervals. This process is called sampling. It results in a set of discrete data points that lie on the curve describing the function. However, the sampled data only consists of pairs of x and y data points. We no longer know what the function looks like between the data points. In order to estimate the area of each of these subintervals, we need two things: the x and y values of the points and an assumption as to what the function looks like between the data points. Next, I'll talk about two different approaches towards determining the data points we need. After that, I'll talk about some common assumptions about the behavior of the function between the data points. During these discussions, keep in mind that, as with numerical differentiation, our approach to numerical integration will be to get a solution that's close enough to the actual integral for engineering purposes. We have two possible ways that our function can be defined: by a functional relationship or by a set of measured data points. Either approach allows us to determine the value of the function at the boundaries of the subintervals. If the function is given, we can choose any values of x we want to define the subintervals and then calculate the corresponding function values. If we're provided with data points, we already have the x and y values of the data points to define the subintervals. We've already discussed the issue of inferring functional values between data points when we talked about interpolation. What we need to do to get the area of the subintervals is also an interpolation problem, in that we're going to assume the function's behavior between given data points. We could, for example, choose to use the data point on the left of the interval as the value of the function within the interval. Or we can use the data point on the right side as the function's value within the interval. Or we can connect the data points with straight line segments. This creates little interval areas that are little trapezoids. So it's called trapezoidal integration, or the trapezoidal rule. There are, by the way, lots of other approaches to numerical integration, but they mostly just boil down to using different interpolation schemes. Keep in mind that the interpolation approach is arbitrary. Some approaches may give more accurate results than others, but generally there's a trade-off between accuracy and computational effort. The better the accuracy, the longer it takes to calculate the integral. Now let's develop trapezoidal integration more thoroughly. Trapezoidal integration is based on a linear interpolation between adjacent points. So the differential area between the kth and the k plus 1th point looks like this. It's just a little trapezoid. Its area is equivalent to the area of a rectangle whose height is the average value of the function at the endpoints, since the area of this little triangle cancels the area of this little triangle. The average value of the function is 1/2 of the sum of the values at the endpoints, and this is the base of the trapezoid. Next, I'll talk about using this expression for trapezoidal area to calculate the total area under a curve. First, I'll use a for loop to implement the algorithm, and then I'll introduce a couple of MATLAB commands which perform the process. I'm going to create a function to implement this process. The inputs to the function will be arrays containing the values of x and f of x at the boundaries of the subintervals. The function will return the total area under the curve, which will be a scalar. Now I'll create some pseudocode. I need to calculate areas for all the subintervals and then add all those areas up. If there are n data points, this results in n-1 subintervals. So I'll have to go through my loop n-1 times. N is just the number of data points that I have, so I can calculate it as the length of either the x or the f vector. I'll arbitrarily base it on the length of f. I know how many times I'm going to go through the loop, so a for loop is probably easier than a while loop. I'll use k as my variable to keep track of which subinterval I'm working on. For each subinterval, I'll calculate an incremental area based on f of k plus 1 plus f of k divided by 2, which is the average value of the function, times the base of the rectangle, which is x of k plus 1 minus x of k. Then I'll cumulatively sum all of the areas by setting int, the value of my integral, to its old value plus the differential area. Finally, I need to initialize int before the loop so that it's defined on the right-hand side of this equation the first time through the loop. The integral is 0 before I start calculating areas. I'll name my trapezoidal integration function trapint.m. Since I'm creating a function, the first line has to be a function declaration statement. My output variable is named int. The function name is trapint, and it accepts two input arrays, x, the values of the independent variable, and f, the values of the function at the given values of x. First, I need to initialize the value of int to 0 and determine the number of points in the arrays. Now I can start looping through the values to get the accumulated area under the curve. For k equals 1 to n-1, I'll condense the calculation of the incremental area and the cumulative sum into a single command. So int will equal int plus f of k plus 1 plus f of k divided by 2, which is the average height of the trapezoid, times x of k plus 1 minus x of k. Now I end the for loop and I'm done. Save the file. Back in the command window, I'm going to integrate the function x squared plus 1 between 0 and 1. I'll use a step size of 0.1 in the x direction, so my x values will be x equals 0, colon, 0.1, colon, 1. The corresponding y values will be y equals x dot caret 2 plus 1. I'll send these arrays to my trapezoidal integration function and return the result as int. The function returns 1.335 as the estimate to the integral. The exact value of the integral is 1 cubed over 3 plus 1, which is 1 1/3. So the difference between the actual integral and my numerical estimate is pretty large. Next, let's take a look at how we can improve this estimate and, maybe more importantly, how we can get a feeling for how accurate our estimate is without determining the exact solution. As long as our assumptions about the behavior of the function are reasonable and we can make our subintervals small enough, we should be able to get a reasonable approximation to the exact integral. However, how can we tell if the result of our integration is close enough to the exact solution since we don't know the exact solution? To answer that, let's take a look at what happens as we reduce the size of the subintervals. Suppose we start with an interval like this. Obviously, these subintervals won't give a very accurate estimate of the integral. Let's cut the width of the intervals in half. Now our estimate's probably a lot better. Also, there's a pretty big difference between the two integral estimates. So let's cut the interval in half again. That should result in a better estimate for the integral. And maybe more importantly, the difference between the integral estimates is smaller than the previous change. As we keep reducing the width of the intervals, we get better accuracy, and most likely the difference between successive integral estimates gets smaller and smaller. A common approach for numerical integration is to choose an arbitrary subinterval width and then keep reducing the width of the subintervals, often by halving the interval each time, and checking to see when the difference between successive estimates becomes small enough to be insignificant. Of course, if the widths of the subintervals become small enough that numerical round-off errors are important, our errors can increase with decreasing widths. There are a couple of MATLAB functions that perform trapezoidal integration. TrapZ works pretty much exactly like the function I created in the demonstration. You send in arrays containing x and y data, and it returns a number, which is the integral of the y data based on the trapezoidal rule. TrapZ performs a cumulative trapezoidal integration. It also accepts as inputs arrays of x and y data, but it returns an array instead of the single number that TrapZ provides. The kth element of the output array contains the accumulated integral from the first to the kth element of the input arrays. Now I'll do a short demonstration to illustrate use of the TrapZ and TrapZ functions and the effects of decreasing the subinterval sizes. I'll use the TrapZ function to see how changing the step size affects my integral estimate. As before, I'll integrate the function x squared plus 1 between the limits of 0 and 1. The exact solution is 1 1/3. For my numerical integration, I'll start by using a step size of 0.1. The values of the function are then calculated with f equals x dot caret 2 plus 1. The syntax to do the integration is int equals trapz of x comma f. My solution is 1.335. This is the same as the solution I got previously with my own integration function, as I would expect. Now I'm going to reduce my step size to 0.05, or 1/2 of what I used before. Repeating the integration, I get 1.3338, which is slightly closer to the exact solution. Now I'll cut the step size by a factor of 5. So x equals 0, colon, 0.01 to 1. And this gives an integral estimate of 1.3334. Cutting that step size by an additional factor of 10 gives 1.3333, which agrees with the exact solution to the 4 decimal places that I'm displaying. By changing the display format to provide more decimal spaces, we can see that the solution agrees with the exact solution to 6 decimal places now. Reducing the step size is giving us more and more accurate results, and the solution is obviously converging to a consistent number. Even if we didn't have access to the exact solution, we could make a pretty good estimate of when we get sufficiently close to the actual solution to the problem. So far, I've presented numerical integration of functions that are specified by a series of data points. It didn't matter whether I had an actual symbolic representation of the function. I just need a bunch of x and y values. This is pretty much how all numerical integration schemes work, though some approaches are more sophisticated than the simple methods used in this video. There are some additional MATLAB commands that perform numerical integration for a specified functional relationship. These commands seem to be doing something very different from the approach I used in this video, because you provide these commands a function rather than a set of data points. However, these commands secretly create data points and use those data points to estimate the integral. So their interface with the user looks different, but it's actually almost the same process as I presented here. I'll talk about these commands and how they work in the next video.